It's already time. Let me wait for 2 minutes if others want to join, and then we will start. In the meantime, if you have anything that you want to ask, any questions regarding the previous sessions, you can unmute your mic and ask. Okay, so I think we can start, and if others want to join, they can join in between. Okay, so yeah, let us start. Let me write down the first question. So we have an atom which is in singlet state. Okay, it is in singlet state and it is subjected to a magnetic field. Okay, the question is the Zeeman splitting of its 600 nanometer spectral line is 0.04 nanometers. Okay, now we have to find the value of B. The options are okay. So let's look at the question again. So we are given an atom and it is in singlet state. Now what do we mean by singlet state? So singlet state means that it is in a state which is very similar to that of a hydrogen like atom. Okay, basically it has a single electron in the outermost shell, correct, just like hydrogen atom. And now we put it in a magnetic field B. Okay, so there is an atom. Okay, there is an atom, let's say here, and then we put it in a magnetic field. Okay, Let's say we have some magnetic field B and we put an atom here. Now, before applying the magnetic field, we had one spectral line. Okay? We had one spectral line, and this was observed at 600 nanometers. And after we apply the magnetic field, this line gets split in two parts, and this separation between them, this is given to be 0.04 nanometers. Okay, and this phenomena is known as Zeeman splitting, right? This was also discussed in the class, that whenever we put an atom in a magnetic field and then we measure its spectra, then there is splitting of the spectral lines. Okay, so here in this case, the spectral lines, they split in two parts, and the separation is 0.04 nanometers. Fine, so this is the question. Now what we want to do is we want to find out the magnetic field B. Okay, so we have the formula for Zeeman splitting. And the formula is delta lambda here. Now we want to find out B, so we can rearrange the terms. Upon rearrangement, we can write B as okay. So this is the formula, and now we know all the values. So here, what is M? Okay. So let's write out. So M is mass of electron, which is 9.11 into 10 to the power minus 31 kg. Okay. C is speed of light. We all know its value is 3 times 10 to the power 8 meters per second. Okay. E is electronic charge. And it is 1.6 into 10 to the minus 19 coulomb. Okay, and then lambda is given to be 600 nanometers, and delta lambda is given to be 0.04 nanometers. Okay, so we can plug in all the values. So we can just plug in all the values and then we can calculate. So our B will become, so this is 4 into pi, so M is 9.11, C is this much, lambda is 600 into 10 to the power minus 9 squared, and delta lambda is 0.04 into 10 to the power minus 9. Okay, and this will come out in Tesla. So if we calculate, we will get 4 into pi into 9.11 into 3 into 0.04 divided by 1.6 into 600 into 600 and into 10 to the power. So here you have minus 31 plus 8 minus 9 plus 19 and then again plus 18. Okay, again we can cancel out these two zeros. So this is 10 to the power 4. So here we will have minus 4. Okay, so then this is minus 32 minus 36 and this is so basically 10 to the 1. So then this becomes 4 into pi into 3 into 0.04 divided by 1.6 into 3.6. Okay, and now if we if we calculate this, so this should come out to be 2.356 Tesla. Okay, so our magnetic field B is nothing but 2.356 Tesla. Which is option number B. Okay, so from this question we can see that to get a splitting of 0.04 nanometers, which is a very small number, right? It is a very small number, and therefore we need very good quality spectrometers to observe this effect, correct? So when we want to observe Zeeman splitting, we need very high magnetic fields. So 2 Tesla is a very high magnetic field. Okay, the small magnets that we use in our homes, right, in the speakers or the common magnets, their magnetic field is of the order of oersteds, right? 1 oersteds, 10 oersteds, like that, and 1 oersted is 10 to the power minus 4 Tesla. Okay, so this is like 2000 oersteds. So this is a huge magnetic field, and it is this amount of magnetic field is generated in laboratories, right, using electromagnets which are very large. Okay, we use generally superconducting magnets like squids to obtain such high magnetic fields if you want to observe such effects. Okay, so this was one problem on Zeeman splitting. Let's do one on the spectroscopic notations. Okay, so let me write down the next problem. Okay, so this is the problem. We are given several spectroscopic terms, and what we are asked is which of these is not possible. Okay, so not possible. Now we know that there is a general formula for spectroscopic notations. What is the general formula? The general formula is 2s plus 1, and then here we have L, and here we have J. Okay, where L can be S, P, D, and so on, and correspondingly we will have L as 0, 1, 2, and so on. Okay, similarly we will have J as L plus S, plus minus S. Okay, okay, fine. So yeah, let's look at all the terms one by one. So let us look at option number A first, which is 2s 1 by 2. So here by comparing 2s plus 1 is 2, which means s is half. Okay, and then here L is s, so this will imply L is 0, and on comparison we get J as half, which we can write as L plus S. So therefore this term is possible. Okay, let's look at option B. Okay, option B is 2p half. Again this is 2s plus 1 is 2, so s is again half. Now here L is p, which means small l will be 1. Okay, and again J is half, which we can write as L minus S. So again this term is possible. Okay, now C is 2D 3 by 2. C is 2D 3 by 2. So again this is 2s plus 1, which implies S is again half. Now this time L is D, so small l will be 3. Okay, now here J is given to be 3 by 2. Correct, J is given to be 3 by 2. And note that this is not equal to L plus S, which is 3 plus half, which is 7 by 2. Sorry, here L will be 2. Sorry, my bad. So then 2 plus half is 5 by 2. Okay, and L minus S is 3 by 2. So 3 by 2. So again this is equals to L minus S, therefore it is possible. Now last option is 2D 1 by 2. Okay, last option is 2D 1 by 2. Here S is as usual half. Again L is D, which will give us L is 2, and J is half here, and we have already calculated L plus S and L minus S in the previous example, which is 5 by 2 and 3 by 2. So we can see that it is not equal to both of them, so therefore it is not possible. Okay, therefore correct option is option number D. Okay, so this was a pretty straightforward problem. We are given a few spectroscopic terms, right? We have SPD, and then from comparison with the, so this is our general notation. Let me write not general but standard notation. This is standard notation, right? So when we compare all these spectroscopic terms with the standard notation, we can extract out the values of small s, small l, and small j just by direct comparison. So the superscript, this gives us the value of small s. The subscript gives us the value of small j, and this alphabet L, this gives us the value of small l. Okay, and then we can check if our L plus minus S, if this is equals to J or not. Okay, so this is how we solve this problem. For the first three case, we see that when you have S or P or D 3 by 2, we can write J as L plus S or L minus S, and therefore these three spectroscopic terms are possible. However, for the last one, we see that J is given to be half, but we cannot write it as L plus S or L minus S. Therefore, this spectroscopic term is not possible. Okay. So let's go to next question. Question number 3. So we are given the wave function for a 1s electron in hydrogen atom, and it is given as, so we have psi, this is equals to 1 upon under root pi a naught cube a to the minus r by a naught. Okay, so this is the wave function which is given to us, where a naught is Bohr radius, correct? Now the question asks us to find the average value or the expectation value of 1 over r for this wave function. Okay, and our options are 1 over a naught, 2 over root a naught, 1 over root a naught, and finally 3 over root a naught. Okay, so we are given a wave function psi. Okay, this is the wave function that we are given, and this corresponds to a 1s electron in hydrogen atom. Okay, here a naught is the Bohr radius, and the answer, if you see the options, is given in terms of the Bohr radius. Okay, so this term which you see in these square brackets, this is a constant, and this is the normalization constant, and this is the exponentially decaying function e to the power minus r by a naught. Okay, so this is how our wave function looks like. Okay, so now what is the question asking us to do? question is asking us to find the expectation value of 1 over r. Okay, so expectation value of 1 over r, so this is generally denoted as like 1 over r. Okay, and we want to find out this value, so the average of 1 over r. Okay, now in the class and also in the previous sessions we discussed how do you find expectation value of any function which is given to you. So here we are given 1 over r, and the formula for the expectation value, let me write down here. We have 1 over r expectation value, so this is just simple integration, and here we write our function which is 1 over r, and then we have mod psi squared dr, right? Because this psi squared is the probability, and this okay, because this is hydrogen, it will not be dr but it will be d tau, right? We have a, it is a three-dimensional problem, so we write this in terms of volume d tau. Okay, now psi is already given to us. Okay, psi is already given to us. Let's write psi here. Our psi is pi a naught cube under root. So this is 1 over, and then we have exponential minus r by a naught. Okay, and now this is the thing. So when we take square of this thing, so this under root will vanish, and this is a constant, so we will take it outside the integral, and inside we will have 1 over r, and then exponential, because we take square, so it will become 2r by a naught. Okay, and this d tau, because now we are writing in spherical polar coordinates. Okay, so in spherical polar coordinates the differential volume element is written as r square sine theta d theta d phi and dr. Okay, like this. So this is basically a triple integral. This is basically a triple integral. Okay, so let's write all the integrals separately. So here we have sine theta d theta, and theta goes from minus pi to pi. No, actually goes from 0 to pi. 0 to pi, and we have d phi, it goes from 0 to 2 pi, and then we have integral over r, which goes from 0 to infinity, and this is 1 over r e to the minus 2r by a naught r squared dr, like this. So this r will cancel out with one of the r's above. Okay, and this will remain same. Now integration of sine theta is minus cos theta, and minus cos pi is minus 1, and cos of 0 is 1. So basically okay, let me rewrite. So this comes out to be minus cos theta, and the limits are 0 and pi. Okay, this is simply 2 pi. It's not, because this is d phi, so this is 2 pi minus 0, 2 pi. And then here we will have integration from 0 to infinity r times e to the power minus 2r by a naught and dr. Okay, so therefore this pi will cancel out this pi. Okay, so this will become 1 upon a naught cubed, and cos, okay, let me write minus cos of pi is -1, okay, and then this becomes plus cos of 0 is 1, like that, into 2 integral 0 to infinity r e to the minus 2r by a naught dr. So this this is 1 plus 1 2 times 4, so this is 4 by a naught cube integral r e to the minus 2r by a naught dr 0 to infinity. Okay, good. So we are getting somewhere now. Now we just need to solve this integral. Let us call this integral as I. Okay, and this we will solve by a technique using by parts. Okay, this is called integration by parts. So here what happens is basically, so our I will become, so we take, okay, so let's say this is our first function r and this is our second function e to the minus 2r by a naught. So yeah, so this basically becomes first function into integration of second function, okay, and then we put the limits from 0 to infinity minus integration of differentiation of first function, which is simply 1, right? So differentiation of first function, this will give us 1, okay, times integration of second function. Okay, and then we have a dr. Okay, so this term will become, so here we will have r, and integral of an exponential function will give us again the exponential function, and whatever we had here like minus 2 by a naught, we need to multiply, I mean we need to divide by the same thing, so we'll have minus 2 by a naught here, like this. So again, as I said, so this just becomes 1, and here this integral, again as we discussed, this will become minus 2 r by a naught divided by the same thing, minus 2 by a naught, okay, dr. So this is it. Now this we can write as minus a naught by 2, right, e to the minus 2r by a naught multiplied by r, and here we have the limits, so this will become plus a naught by 2 integral 0 to infinity e to the minus 2r by a naught dr. Okay, so this is just some calculations you can even do on your own if you're unable to follow what I'm doing, just solving basic integrals. Now when we put limit infinity in this function, so we get e to the minus infinity, correct? So this term just basically goes to 0, and when we put 0 in this function r, so this becomes 1 and this is r, so then this term again also goes to 0, so the first term basically vanishes, so this is 0, okay, and here we have a naught by 2, and again integration of this we have already done multiple times, upon minus 2 by a naught, and we have to put the limits 0 and infinity. Okay, so now this term has vanished to 0, and we are only left with the other term, so we can rewrite this as minus a naught squared by 4 e to the minus 2r by a naught, 0 and infinity. Now again, when we put infinity in place of r, and we know that e to the minus infinity is 0, okay, so this becomes minus a naught squared by 4, 0, and when we put 0 here, so e to the power 0 is 1, so we get minus 1. Okay, so this simply becomes a naught squared by 4. Okay, so this is the value of I. We are calculating I, correct? And this was our expectation value of 1 by r. So now we will just substitute. Let's say this is equation 1, and in equation 1 we will substitute the value of I. So using equation 2 in equation 1, we get expectation value of 1 over r. This is nothing but, here you can see 4 by a naught cube, 4 by a naught cube multiplied by a naught squared by 4. So 4's will cancel out, and this a squared will cancel out this cube, and we will be left with only 1 by a naught. Okay, so finally we can write 1 over r is 1 by a naught. And this matches which option? Option A. Okay, so yeah, this was a little lengthy problem, but very straightforward problem. If we know how to solve integrals, then we should not have any difficulties handling this problem. We are given everything. We are given the wave function psi, and we are asked to calculate the expectation value of 1 over r. Now because this is a hydrogen atom, so we must use, because this is a spherical system, right? So this is hydrogen atom, and we know that this is a spherically symmetric system. Therefore we are using spherical polar coordinates, and if we know how to write d tau in terms of spherical polar coordinates like this, and then separate out integrals for d phi, d theta and dr, we get to this equation 1. Now in order to solve equation 1, we use technique called integration by parts, and here we assign basically numbers to the two functions. We call them as function 1 and function 2, and there is a rule known as ILATE. So in case you are not comfortable with this, you can Google or refer to any calculus textbook, and yeah, it is a very standard technique that we use. So here basically once we have named our functions as 1 and 2, then what we can do is we can write our integration I as first function into integration of second function minus differentiation of first function times integration of second function, and then integrating over the entire thing like that. And then it's just matter of putting the limits, and then we get a value of I to be a naught by 4, which is equation 2, and then we just substitute the value of equation 2 in 1, and we get the expectation value of 1 over r. Okay, any doubts in this one? No? Okay. Then I think we can proceed to the next problem. Again, this problem is again related to hydrogen atom. So this will be problem 4. So the question is normalized radial wave function. So normalized radial wave function of H atom for n is equals to 1 is given as two by a naught this thing a to the power minus r by a naught. Okay, again a naught is the Bohr radius, just like in the previous problem. Now note that this is only the radial component. Okay, only radial wave function is given. In the last question we had the entire wave function which had the theta component and the phi component, but here this is only the radial component, and therefore its normalization constant looks a little different. Okay, so the question is find the ratio of probabilities of R for R equals to A naught and R is equals to 3 A naught. And then we are given some options. 1:3, 9:1, 6:1, and √3:1. Okay, let me have some more. Okay, so anyways we are given the radial wave function. And you can see that it is an exponentially decaying wave function. So maximum probability is at r is equals to 0, and then 0 probability at r is equals to infinity. Okay, why? Because probability P of R, this is defined as R squared, like this. Right? So this is how we define the probability when we are given a radial wave function. So this is the formula. Okay. Now we have two cases. So case 1, R is equals to A naught, and case 2, R is equals to 3 A naught. And we have to find the ratio of probabilities for both these cases. Okay, so yeah, let's begin. So let's find out probability for case 1 when R is A naught. So then this becomes A naught squared. Okay, before that, let us also calculate mod of R squared. Okay. So let me check this little bit. Yeah, okay. So what will be mod R squared here? So it will be 2 by A naught 3 by 2 squared, and e to the minus 2R by A naught. So this will be 4 by A naught cube e to the minus 2R by A naught. Okay. So when R is A naught, so this simply becomes e to the power minus 2. Fine. This becomes e to the power minus 2. And P2, when R is 3A naught, so this becomes 3 squared is 9. And then here you will get e to the power minus 6. Yeah, like this. So if we solve this, this will cancel out with this, and we have 4 by A naught e to the minus 2, and again this A naught will cancel, and here we have 36 by A naught e to the power minus 6. Okay, now ratio of probabilities. This is what the question asks us, right? Ratio of probabilities 1:2. This will be P1 divided by P2. Okay. And here we have P1 and P2. So this simply becomes 4 by A naught e to the minus 2, and then A naught by 36 e to the power 6, like this. Okay, so this A naught will cancel out. This will become 1/9. So this becomes 1/9 e to the power 4. And e to the power 4 is 54.6 divided by 9. So this comes out to be very close to 6:1. Let's see if it is matching with any of the options. It is matching with option C. 6:1. Okay. So therefore what it means is that when we are given a wave function, radial wave function for n is equals to 1, then it is 6 times more probable to find the electron at r is equals to a naught than at r is equals to 3 a naught. Okay, so the probability decreases exponentially, and it is 6 times the probability at r is equals to 3 a naught when the electron is at r is equals to a naught. Okay, so yeah. Well, I guess we will solve a simple problem for the next one. Okay, so this is the next problem which we are going to solve. We are given orbital quantum number L as 2. Okay. So we are given L is equals to 2, and we are told that the electron is in the presence of external magnetic field. Okay, so there is an external magnetic field which is applied. Let's say that the external magnetic field is applied in z direction. Okay, let's say this is the direction of applied magnetic field. Now the question asks us as how many orientations of orbital angular momentum L is possible. Okay, orientations of orbital angular momentum L. Okay, so orientations of orbital angular momentum L. This is what we need to find out. Okay, so now other thing that we know is we have magnetic quantum number, magnetic quantum number n. Okay, and the value of m, it starts from -L and then it gets increased by 1 and it keeps on increasing till we reach L. Right? So this is the thing. So when L is 2, our M will be minus 2, minus 1, 0, 1, 2. Okay. Now, what is the meaning of magnetic quantum number? So when you multiply this magnetic quantum number by h cut, okay, so you will get m h cut. This is nothing but component of orbital angular momentum L. So this is component of L along B. Okay. So for example, when m is 0, it will not have any component along the applied magnetic field B. So our angular momentum will lie in this orientation. Okay, this corresponds to m is 0. Similarly, when m is minus 1, when m is, let's say, plus 1, when m is plus 1, so this L will, okay, let me draw it like this. When m is plus 1, so our angular momentum L will have component h cut in this direction. So this is when m is 1. Similarly, it will have 2 h cut like this, and then minus h cut and minus 2 h cut like this. So therefore, in total, we will have 5 components. So the correct option is 5. Now note that we can take any of the component. And it will precess around the z-axis, which is the direction of applied magnetic field, in a circular way. Okay, so this angular momentum precesses around the magnetic field and it will not align with the magnetic field. It will always have some orientation with respect to magnetic field, and these orientations depend on the value of L and the value of M. Okay, I hope that makes some sense. So if it does, I think we are ready to move to the next problem. So this is more of a refresher. This is a very simple problem which checks our clarity of concepts and if we remember what we learned in our earlier classes. Okay, so question is that an electron is revolving. Which is revolving in xy plane in clockwise direction. So it is revolving in the clockwise direction, and what we are asked is find the direction of angular momentum vector L. and our options are along positive z-axis, along negative z-axis, along positive y-axis, or along negative x-axis. Right? So let us first draw the Cartesian coordinates. Okay, then let's draw a circle in the xy plane like this, and the electron is moving in the clockwise direction. So if we have electron, it is rotating like this. Okay, so it is rotating like this, and this is also the direction of your velocity. So this is the direction of velocity. We can also draw position vector, and this position vector is called r, okay, which we'll be needing later. Okay, fine, yeah, looks good. Now how do you define angular momentum? So L is nothing but r cross p, or we can write it as m times r cross v. Okay, so notice that we can take a special case when, let's say, our r is pointing along y direction, okay, which will be this case. When r is like this, okay, when r is along plus y, our v is along, so velocity will be like this, which is plus x. Now y cross x, y cap cross x cap, this gives us minus z cap. Okay, okay, therefore L is along minus z axis. So correct option is B. Right? Now, if you do not want to calculate the cross product, there is also a much simpler way to do it. Okay? Easier way, we use a right hand thumb rule. Okay, so what is right hand thumb rule? That we curl our fingers in the direction of rotation, and our thumb will point in the direction of angular momentum. So in this case, because it is moving in the clockwise direction, so our fingers will curl in the clockwise direction like this, and therefore our thumb is pointing downwards, which gives us the direction of angular momentum as down. If it was moving in anti-clockwise direction, then we will curl our fingers in the anti-clockwise direction like this, and our thumb will point up, which is the plus z direction. Okay, so this is the other way of solving this problem, which is using the thumb rule. Okay, good. Let's get back to Z-man effect now, and let's solve one problem related to Z-man effect. We started this session with a problem on Z-man effect where we calculated magnetic field, and we said that we need very high magnetic field to get Z-man splitting, right? So now let's see one more problem. Okay, this will be problem 7. Okay, again this is problem of Z-man splitting. Okay, we have a normal Z-man splitting. We are given the wavelength of the spectral line, okay, and we are given magnetic field of 5 Tesla. Okay, so as we discussed earlier, we have a wavelength lambda of the spectral line, and when we apply a magnetic field, this gets splitted in 2 spectral lines, and then this distance, this is delta lambda. Okay, just as we discussed in the first problem. And now if you remember the formula from the first problem, we have delta lambda as okay, let's derive this formula. So the formula for Z-man splitting is generally written in terms of nu. Okay, so let's write in terms of nu, doesn't matter. So this is E by B. and divide by 4 pi m. Okay, this is the formula, okay, where nu is the frequency and this is nothing but c by lambda. Okay, now to derive the formula for delta lambda, what we are going to do is we are going to write the value of log nu. This will be log c minus log of lambda. Okay, now when we differentiate this equation, upon differentiating, okay, so because c is a constant, so it will just vanish away, and differentiation of log x is 1 over x, so this will become delta nu over nu will become minus delta lambda over lambda. Okay, this will become delta nu as minus nu by lambda delta lambda. Now we know that nu is c by lambda, so this becomes minus c over lambda squared delta lambda. Okay, so now if we substitute this value of delta nu in the first equation, we will get delta lambda, only the magnitude, so we can forget about the negative sign because we are taking the difference. Okay, so delta lambda will become e b lambda squared upon 4 pi mc. Correct? So this is what we have. Now again we are given b as 5 Tesla. Okay, b is 5 Tesla and we are given lambda as 4250 angstroms. 4250 angstroms. Okay, now here E is nothing but charge of electron, M is mass of electron, and C is speed of light. So we can just plug in all the values and we will get delta lambda as, so this is 1.6, this is just 5, this is 4250 squared, and we'll have minus 20 here. So this entire thing divided by 4 pi into 9.1 into 10 to the power minus 31 and 3 into 10 to the power 8. So this is the expression which we need to solve. Now note that the answer is asked in angstroms, so we can just take out 110 to the power minus 10. Okay, so we can just multiply by this and then our answer will be in angstroms. Okay, so this will come this thing into 4250 divided by 4 pi into 9.1 into 3, and here you will have minus 19 minus 20 plus 10 plus 31 minus 8. So this thing. Okay, so this becomes minus 39 and plus 31 becomes minus 8. Minus 39 plus 31. Yeah, so this is minus 8 and then this is minus 16. So basically 10 to the power minus 6. Okay, so this entire thing is nothing but 10 to the power minus 6. Okay, so this simply becomes 4.25 divided by 4 pi into 9.1 into 3 angstroms. Okay. So let us solve this thing. I'll use a calculator. X into 5. So our numerator becomes 144.5 and our denominator becomes 343.06. So now if we do this, we get 0.421 angstrom. Okay, so delta lambda is 0.421 angstroms. Let us check the options. Okay, it matches with option A approximately. Okay, yeah, so again you can see that this is very small separation of 0.426 angstroms, very small separation, and to get this separation we have to use a very high magnetic field of 5 Tesla, just as we saw in question number 1. Okay, yeah, so here the other thing that we did, that if we have a formula in terms of delta nu, we can convert it to a formula in terms of delta lambda or the wavelength. Okay, and how we do that is we change from mu to delta lambda by taking help of this log function, and then we differentiate the log function. Okay, good. So this was question number 7. Let us solve one more problem regarding orbital angular momentum, which will be question number 8. Okay, this is question number 8. Okay, and here we are told that we have total angular momentum capital L. Okay, and this is for a hydrogen atom. For a hydrogen atom, we are given total angular momentum L, and this hydrogen atom is under the influence of an external magnetic field B, which is applied in z direction. Okay, this is applied in z direction, and now the component of L in z direction. Okay, so the question is about the component of L in z direction. If you remember one problem before, we solved a very similar problem where we found possible orientations of L in presence of a magnetic field. Here, instead of orientations, the question is about the component of L in the z direction. Okay, and the options are that the z component may be equal to magnitude of L, always less than magnitude of L, always greater than magnitude of L, or all of the above may be possible depending upon the value of B. Okay, so let us write down few things. So here the question talks a lot about magnitude of L. Okay, magnitude of L, magnitude of L. Now what is the magnitude of L? Let us write down first the magnitude of L. Magnitude of L. This is given by, if anyone remembers correctly, under root L plus 1 multiplied by h cut. Okay, this thing. And the component along Z is given by m h cut, where m goes from minus L all the way up to plus L. Okay, and somewhere here it will also be 0, like this. So when will be the component along Z maximum? Okay, let's write component along Z is maximum when m is equals to L. Okay, this is correct. So we can write maximum component along Z, this will be L times h cut. Okay, so this is L times h cut. Now if we compare these two, comparing L h cut and under root L plus 1 times h cut, so which is greater? So this under root L plus 1 will always be greater than L, right? This will always be greater. Why? Because this thing we can rewrite as under root L times L, and this is under root L times L plus 1. And since L is less than L plus 1, so L h cut is less than under root L plus 1 h cut. Okay, and therefore Therefore, the z component of L, which I am writing here as Lz, is always less than L. So which matches with our option B. Okay. So now if we go back to the previous problem, yeah, this one, question number 5. So here, if you see, here L was given as 2, so this is d electron. When electron is in d orbital, you can see that the maximum component of L along Z is 2h cut, right? So this is 2h cut. So maximum Lz is 2h cut, whereas the magnitude of L, this will be under root 2 times 2 plus 1, which is 3 h cut. So this is under root 6 h cut. Okay, and what is the value of root 6? Let me check quickly. So root 6 is, so this is roughly 2.45 h cut. Okay. So for example, for a d electron, our magnitude L is 2.45 h cut and Lz maximum is 2 h cut. So the z component is always less than the magnitude of L. Okay, this was the question. So let's move on to the next problem. Okay, so this is the problem. Now we already know about the spectroscopic notation. We already discussed previously that this is the standard notation. Okay, this is the standard notation. And if we compare it with 4D half, we get 2s plus 1 is 4, and we get L is 2 and J is 1 by 2. Okay, so this basically means that 2s will be 3 and s will be 3 by 2. So let us rewrite this as s is equals to 3 by 2. And j is L minus s, so 2 minus 3 by 2, which will give us 1 by 2. So all good. Now what about Zeeman splitting? So the Zeeman splitting delta E in presence of weak magnetic field is given as delta E is equals to G times Mj EH divided by 4 pi M multiplied by B. Okay, where G is 1 plus Jj plus 1 plus Ss plus 1 minus Ll plus 1 divided by 2j j plus 1. Okay, so this is what we have already learned in the class, that whenever we apply a weak magnetic field, the amount of Zeeman splitting that will happen, delta E. Okay, we can write this delta E in terms of h nu, and that will become h delta nu. So this h will cancel out. Okay, so what I'm saying is we can write delta E as h delta nu, and this is then just equals to EH upon 4 pi M times B. So if we cancel out the h, what we are left with is G this thing. Now if you remember, for normal Zeeman effect, we already solved one problem where this is just EB upon 4 pi M. Okay, so here this thing, this is just normal Zeeman effect, but now when we put it in a weak magnetic field, then we get one extra factor here, and this is what we want to compute. Now this is G. What level are we given? We are given 4D half. Let's keep it like this. For 4D half, we know that S is 3 by 2, L is 2, and J is half. Therefore, if we calculate G, it will be 1 plus half, half plus 1 plus 3 by 2, 3 by 2 plus 1, minus 2, 2 plus 1, and divide this thing by 2 into half, half plus 1. Okay, this is the value of G that we will get. So now once we have this, we can basically write 1 plus, this is half into 3 by 2 plus 3 by 2 into 5 by 2 minus 6. Divide by, so this 2 and half will cancel out and we will be left with 3 by 2. Okay, now 1 by 2 into 3 by 2, this becomes 3 by 4 and this becomes 15 by 4 minus 6 divided by 3 by 2. Okay, so 15 plus 3 is 18 and 18 by, so this will become 18 by 4 minus 6 divided by 3 by 2. Okay, so therefore this will become 18 minus 24 divided by 4 into 2 by 3. So this just becomes 2 will cancel out, this becomes 2 and therefore this will become 1 plus minus 6 by 6 because 2 times 3 is 6 and so this becomes 1 minus 1 and this becomes 0. So therefore G is equals to 0 for 4D, yeah, for 4D 1 by 2, and this implies that delta nu, which is nothing but delta E by H, this will be 0. Okay, and this implies no splitting. No splitting. Okay, so the question asks in how many sublevels. So we want to tell them how many sublevels. The term this will split in presence of magnetic field. So the answer is 0. Okay. So what have we done in this one? We have taken the notation. Okay. And then we have extracted. So extracted the values of S, L and J. Then we know that Zeeman splitting delta E in presence of magnetic field. This is given by this equation where G is Landy factor and G is given by this equation. Okay. Now once we have extracted the values of J, S and L, all we need to do is put in the values of S, L and J in the equation for G and find out the value of G. Okay, so once we started with this thing, finding out the value of G, the value of G comes out to be 0. So in this equation, if we put G as 0, we get delta E to be 0. Okay. Similarly, in this equation, we get delta nu as 0, and therefore we conclude that this spectroscopic term 4D1 by 2 does not split into any sublevels under the action of a weak magnetic field. Okay. If that is clear, let's move on to problem number 10. Question 10. So question 10 is related to Ellis coupling scheme. Okay. So this is the problem, and we are given two non-equivalent p electrons. Okay. So we have, let's say this is one p electron, this is another p electron, and these are non-equivalent. Okay. And now what we have to do, we have to couple them using Ellis coupling and then find out the spectroscopic terms. Okay, so let's do it. Let's write for first p electron, let us write S1, this will be half, and L1, this will be 1. For second p electron, okay, let's write here. For second p electron, S2 is half and L2 is 1. Basically both are p electrons, so their values of S and L will also be the same. Now what do we mean by LS coupling? That is the main crux of this problem. So LS coupling means that compute total L and total S of the electrons and then couple them. Okay, so first compute the total L, which will be L1 plus L2, and total S, which will be S1 plus L2, and then we couple them. The other scheme known as the JJ coupling. In JJ coupling, what we do is we couple the S and L first. So we'll have J1 will be L1 plus S1, J2 will be L2 plus S2, and similarly we calculate the total angular momentum for all the electrons before we couple them, and then that is known as JJ coupling. But here we are talking about LS coupling. So our total S will be S1 plus S2. Okay, and so this will be S1 minus S2 gives us 0, and S1 plus S2 gives us 1. Similarly total L, so 1 minus 1, so it goes from L1 minus L2 all the way up to L1 plus L2. Okay, so this will then be 0, 1 and 2. Therefore we will have 6 cases. Yes, so we will have 6 cases for all the values of S and L. So when our S is 0, we will have 3 cases. Okay, we will have 3 cases, that L is 0, L is 1, or L is 2. Then when S is 1, we will again have 3 cases, L is 0, L is 1, and L is 2. So this will imply that J is 0, this will imply J is 1, and this will imply J is 2. Similarly, this will imply J is 1, and this will imply that J can go from 0 all the way up to 2, and again this will imply that J can go from 1, 2, 3, like this, like this. Okay, now we can start writing the spectroscopic notations. Also note that when S is 0, so 2S plus 1 is simply 1, and for this case it is 3. 2S plus 1 is 3. Okay, so we have done all the difficult part. We now just have to write the spectroscopic notation using the standard notation that we use. So 2S plus 1 is 1, so we will get 1 here, and L is 0, which means we will get S, and J is 0, which means we can put a 0 here, and this we can also write as 1S. Okay, Similarly, again s is 0, which means 2s plus 1 is 1. Let's write 1 here. L is 1, will give us p, and this is 1, so we can also write this as 1p. Again, we will have here 1 because s is 0. Okay, and L is 2, which means D, and again 2, so 1 D, like this. Okay. Now when s is equals to 1, so 2s plus 1 is 3. Here we will have 3. L is equals to 0, means here we will have s, and j is 1, so we will write 1 here, and so this we can write as 3s. Okay, so again 3 because s is 1, L is 1 means p, and j can have all these values 0, 1, 2. Therefore we that is why we have 3 here, because this is known as multiplicity, which means that j can have 3 possible values, and this rule does not hold for s orbital, where j will always have just one value. Okay, so in short we can write this as 3p. And finally, again this will be 3, and this will be d, and this will be 1, 2, 3, or in short writing this as 3. Okay, therefore for two non-equivalent p electrons, we get the following term. One s, 1p, 1d, 3s, 3p, and 3d. Okay, okay. So this is our answer. Let's see if it matches with any option. Okay, so these two are clearly not there. Here we have 1s, 1p, 1d, 3s, 3p, 3d. So this is the correct option. Let's check this one. 1s, 1p, 1d, 2s, 2p, 3d. No. So we do not get these two terms. So therefore this option is wrong. Okay, these are all correct. This is wrong, and these are all correct. Okay. So yeah, the question asked about LS coupling scheme for two non-equivalent p electrons. Okay, so we take two non-equivalent p electrons. Let's say this is the first one, and let's say this is the second one. Then what we do is we write down the values of S, which is the spin quantum number, L, which is the total quantum which is the orbital quantum number for both the p electrons. Now for LS coupling scheme, we find out the total spin quantum number S, which is S1 plus minus S2, so 0 and 1, and total orbital quantum number L, which goes from L1 minus L2 all the way up to L1 plus L2. Therefore, we get two values of S and three values of L, and then we make all possible combinations of S and L. So we divide this in two cases, when S is 0 and when S is 1. So when S is 0, L will have all three values. Corresponding to all three values, we find the spectroscopic notation. When S is 1, again L will have all three values, and we again find the corresponding spectroscopic notations. Having done that, we can write all the spectroscopic terms. We see that we are getting 6 terms, and hence we get our answer. Okay. So yeah, that's time. Okay, not many of you joined today online, but I hope these video sessions are helpful in at least in solving your assignments, and I hope you are learning something from it. So I'll upload this on YouTube. These tutorials happen every Saturday from 3 to 5 p.m. I would really appreciate if you join them online and we have a discussion. You can also ask your doubts in these sessions regarding these problems or previous assignments which have been created, and we can have a healthy discussion. Okay. Anyway, if you have any doubts, feel free to leave a comment in the forum or even on YouTube, or you can also email me on my email ID, which is manavanival, my name, @iisc.ac.in. So thank you for listening. I'll end the session now. Bye bye. See you.